effect. Think about non-interacting electrons in a uniform magnetic field, but in 2D with no impurity. So in quantum mechanics, what you know is that energy levels in a magnetic field are quantized into lambda levels, the discrete set of energies, and these energies are given by constant times the frequency times n plus a half, where n is equal to 0, 1, 2, 3, and this new c is the cyclotron. It's just the energy levels of a harmonic oscillator, because classically these electrons will be moving in circles at the cyclotron frequency, and the energy levels are quantized for quantum mechanics. Now, there are many places I can put my orbits, and it turns out that the number of independent orbits in each of these lambda levels is precisely quantized, and the number is equal to basically the number of magnetic flux levels. And that's basically given so that it is basically it says that if I have just one electron per flux quantum, the density flux quantum is given by the proportion of the magnetic field and the electric charge of the area of the sample divided by h. And so it's convenient and very important that this quantity f that we're going to be talking about a lot is the ratio of the number of electrons to magnetic number of magnetic flux quantums. So it's proportional density divided by magnetic field. And what happens is that an integer, what effect happens when this f is an integer. So there's an integer number of electrons per flux quantum. That means a certain number of lambda levels are completely filled, and then the ones above them are empty. There's a gap, which is the cyclotron frequency between the filled and the empty states, and so therefore there's an energy. And in that case, what you find is that you have a quantum Hall effect where this integer nu is just the third fraction number of lambda levels. And, well, okay, so this roughly shows you the energy levels in an ideal system. Then, so here's one lambda level that's filled, here's another lambda level, here's the Fermi level. All of these are filled. This is what happens to the bulk of the sample, at the edges of the sample. It's a bit different, but we don't have to worry about it. Okay, so now what about the fraction states? Fraction states are totally different because now they are where the non-interacting electrons, so we have Fermi level, it's in the middle of the lambda level, so there's no energy gap at all. Well, there's thousands of different states that all have the same energy, and some of them are filled and some are empty. So it's highly degenerate, nothing like what you need. But when you put the electron-electron interaction in, of course, that splits this energy. So you get energy gaps. But what kind of energy gap do you get? And you try to do a simple Hartree-Fock approximation to figure out what's going to happen with its charge density waves. Nothing that looks like what was going. The earliest explanation came from a year after the discovery and general ways of understanding things that were introduced by Jane in 1989. And I'm going to talk about a slightly different approach, which is it's also it's more generalized, so-called positive fermion approach, which I call also the fermion Simons approach. It's introduced by these people in 1991. And, but I'm going to try to explain it at least try to give the flavor of what's done. So the idea is that so we can't solve the problem directly. We're going to try a trick by making a unitary transformation to by multiplying. It's basically a gauge transformation. We multiply the wave function by a complex phase factor, which is basically the product of all the electrons. We talk about the electron position in complex coordinates. So Z is equal to X plus IY, which is electron. We take the difference ZI minus ZJ for a pair of electrons and divide by the absolute values, which is the phase of the orientation. It's a phase factor that depends on the relative angle between these two. And we take this to some number 5 kilometers, it will be just 2 for us. It has to be even integer. This is an even integer that when I take interchange to particles, it doesn't change. So it preserves the Fermi statistics. And then your spin, so the electron wave has to be symmetric, right? Change to particles, and of course, it should have made a Schrodinger equation, the original one. But if I make a gauge transformation like this, I have to also change my Hamiltonian to unitary transformation. So the transformed Hamiltonian, it looks like the original Hamiltonian, which is the units where the electric charge is -1, H bar is 1. So we have magnetic energy, which if they would ordinarily was P plus A is the vector potential squared over 2M plus an interaction, which is the position. And now, because of this transformation, we have to add an extra piece to the gauge, extra gauge piece, which is the vector potential A, which depends on the position of all the electrons, and it's given by this formula. But if you take the curl of this A, what you find is the magnetic field is 0. The curl of this A, this A is something called Chern-Simons. The potential curl of it is what we call so Chern-Simons magnetic field. It's a fake magnetic field, but it acts on these transformed electrons just as over a real magnetic field. And curl of it is just 2 pi times 2 times the density of electrons. So it's 0 everywhere except where I have an electron. And where I have an electron, then there are 2 flux quanta attached to each electron. So the fake, two of these fake flux quanta attached to each electron. And now that's still not a solvable problem, but I can now try to apply Hartree-Fock beam field approximation to this. And now this is easy to work. So what happens in this case, when I take the average fake magnetic field, which is just equal to 4 pi times the density of electrons, and now what I want in Hartree-Fock, we just replace the Coulomb interaction by the average potential, which will just make it 0 constant. And so what in this mean field theory, what we now have 3 fermions in an effective magnetic field, which is the difference between the real magnetic field and this fake average magnetic field. That's this formula here. Applied magnetic field, this is the fake magnetic field, and they have opposite signs in both the charge electrons. So now, what I can do is define an effective filling factor, which is 2 pi times the density of electrons divided by this delta B. And I compare that with the original filling fraction, which is 2 pi times the density divided by B, this will be the number of electrons per flux quanta. This is the number of electrons per fake flux quanta. Effective. And now, you can see that there's a simple relation between them. 1 over P, I invert, this is proportional. 1 over F proportional to B, 1 over P this. And so 1 over P is equal to 1 over F minus 2, or there's a simple relation that the true filling fraction is equal to P plus 2P plus 1. That's the relation between the true filling fraction, fake filling fraction, and now you can see what happens if I'm in a situation where the fake filling fraction is P is an integer. So I filled an integer number of these fake level levels. Then, in the absolute value, P can be positive or negative. Then you might say, okay, well, in the P field theory, there should be an energy gap, a cyclotron gap, in this effective magnetic field. And then that's a stable situation, and maybe that will give you a Quantum-Hall effect. Quantum-Hall effect. But the true electron density is not P. The true electron density is given by this formula. F is equal to P over 2P plus 1, where P is an integer, so this is a fraction with odd denominator. So this at least is a hand-waved mean field explanation for how you can get fractional quantized voltages. Of course, it's hand-waving, and you have to do better, but this is a very good start. And it turns out that this really explains most of the fractions that have been seen. Okay, that's what I want to say about single layer. Now double layer. So as I said, we have 2 layers separated by an insulator, no tunneling. We're going to go tunneling between the layers, but it's cool of interactions. And the nice thing about this is that when it's a good insulator, we can make separate contacts to the 2 layers, and also you can control separately the gates, the electron density between layers, and you can measure a lot of the things that you couldn't measure with a single layer. So one of the things you can do is you can inject the current into one layer or the other layer, and you can make voltages in either of the layers. So one of the things you can do is a drag experiment. For example, I can have a situation where I have a current contact to just the bottom layer here. I run a current to the bottom layer. And no current is allowed to flow to the upper layer because it's only voltage. Now I can measure the voltage drop in the x direction in the bottom layer, or I can measure the top layer. Similarly, I can measure the wall voltage in the top layer and the bottom layer. And so you can see that in principle, I can form the ratio of the current. So this way I can measure 4 different resistances. Drive, resistance in the form of the drive layer and the drag layer. The drag is the one where the current goes in this one, and I measure this. That's 4 different quantities that I can measure. And I can repeat this using the top layer. So that's 8 quantities. Okay. Now it turns out that the drag, but there's a theorem that says, Einstein theorem that says the drag has to be the same in the 2 layers. So there are really only 6 measurements, and of course the top layer and the bottom layer are similar to really only 4. There are at least 4 different things that you can measure. And one of the things that was most remarkable that was discovered sort of seen experimentally by Jim Eisenstein in gallium arsenide double layers is something that I call the integer quantized voltage, which happens when the total, you have some fractional filling in the top layer, some fractional filling in the bottom layer, but the sum of them is exactly 1. So the total is equal to 1. And he observed something quantized voltage. So what's happening? Here's a picture from one of his papers. So again, we have now current in the bottom layer. We're measuring now the so in the quantized in the whole state, the longitudinal resistance will be 0. Will actually be 0, just like. And so what's really interesting is the whole resistance. So this is the 1 over the filling fraction. So this is when the total filling fraction is 1. This is when the total filling fraction is 2. The total filling fraction is 2. You have basically 7 whole states in each layer. So when I run a current through, if I run a current in the bottom layer, I get a quantized wall conductance resistance of precisely h over e squared in the bottom layer, but I get nothing in the top layer. There's no drag. And I vary it. Now look what happens with 2 totals equal to 1, so it's approximately 1/2 in each layer. Suddenly I get this new state where the wall drag jumps to be h over e squared, and the ordinary drag it varies and then it comes down, so it's h over e squared. So in both layers, it doesn't matter which layer I measure the voltage drop is the same. It's independent of which layer or which current is flowing. and it's precisely quantized at h over v squared, which is remarkable. You don't actually have to have exactly u equals 1 units to half each layer, as long as it's right. And, so let me just, this is something that we can understand without using composite fermions, or this. It's actually simpler than the fraction flow thing, but it's a little different. I'll just go through very quickly. Basically, it can be understood in Hartree-Fock if you think about the layered degree of freedom as a with some variable like the pseudo-spin variable 4, and then you can define operators to x, to y, to z. To z tells you whether the upper layer or lower layer, and to x, to y, like how the spin matrices, which mix them, and you can characterize a state by the expectation value for this 4, which is a sphere, and the Hamiltonian. Okay, and so what happens is this constant, you get a broken symmetry state. It's basically a simple integer that one takes most of you have one electron per flux. It doesn't matter whether the top layer or the bottom layer. I can also have things that are in a linear superposition of being the top layer and the bottom layer. As long as they all have exactly the same phase, they're all in the same state, I still get the same Hartree-Fock exchange engine. This, if you think about this, if you have not 50% each layer, then block this vector is someplace in the xy plane. It doesn't matter where the xy plane is, so you have this degree of freedom that allows chain, and you most think about this as a Bose condensation of excitons, where you have pairs of, in each case, if you have an electron in the bottom layer and the hole in the top layer, vice versa. And we can talk about this in terms of phase wave function properties of the system are very similar to that of a superconductor, a superfluid of excitons. Excitons flow without any resistance, either Hall resistance or there's neither Hall resistance nor an ordinary resistance, and just the voltage is the same in the two layers. But and you can have current flows in opposite directions in the two layers. It goes without resistance. Okay, and this has been seen now in graphing in front of me. So let me finally get to the new stuff, fractional. So the new fractional one has four states. These double layer system. In this case, we were going to have an energy gap such that the filling fraction in each layer is fixed. You can't vary. It's not just some of them. Now it's fixed separately. Each of the two layers, and there's an energy gap. There'll be one wall resistance. The longitudinal resistance will vanish. So the current in one layer, there's no voltage drop in the x direction in either layer, but there will be a Hall resistance in the drive layer, and a Hall drag, and they'll both be quantized. They'll be quantized, meaning they're going to be rational multiples of h over v squared, but unlike what I showed you before, in this case, they'll be different. They won't be the same, but they'll both be quantized. And so this is sort of, these are the most prominent ones, fillings that have been seen where these extra states that have been seen in the with the Harvard group